The Institute for Experiential AI is proud to invite you to our spring seminar series, featuring leading AI experts and researchers sharing cutting-edge ideas. You can expect AI leaders from a broad range of industries sharing perspectives on defining and applying ethical AI in our distinguished lecturer series, and EAI faculty and Northeastern University researchers discussing their AI research in our Expeditions in Experiential AI series. Up next, join us with Jimmy Lin, Professor of Computer Science at the University of Waterloo, for his seminar, Information Access in the Era of Large Pre-trained Neural Models, on Wednesday, April 26, 2023 at 1 p.m. Eastern, online or in person at the Curry Center, room 440 at Northeastern University. Registration is required and the seminars are free to attend. We hope you'll join us for an invigorating spring semester.
Hey, so my name's Ken Church, and I'm here to welcome Jimmy Lin. It's my great pleasure to have Jimmy Lin here. Just a second. Too many things going on. Anyway, Jimmy and I go way back, and it's really, I remember when I was at Hopkins and you were at Maryland, you asked me to give a guest talk in one of your classes. Do you remember the first question that was asked? I'll never forget this question.
I actually don't.
I'm sure you wouldn't. So the student wanted to know whether anything I was going to say was going to be on the final.
And what did I say?
I think you said it wasn't.
Oh.
And then I lost the audience.
Yeah, and they just went to sleep afterwards.
At any rate, so I think none of this is going to be on the final. So please take it away.
Okay, so that's permission for you to all zone out, I guess. All right, so let me start at the top. So what is the problem that we're trying to solve? And by we, I mean myself, my research group, and the research community that I'm part of. All right, so it's rather simple. We want to figure out how to connect users with relevant information. Now, as it turns out, this is a relatively modest endeavor in the sense that I really don't care that much about building AGIs, artificial general intelligences, whatever those are. I'm not particularly interested in unraveling the mysteries of consciousness or how babies learn based on limited information. I want to tackle pretty simple tasks. You got users, you got information they need. How do we connect them? Right. So in terms of academic silos, this is generally referred to as the community for information retrieval, dealing with search, but it also encompasses things like question answering, summarization, recommendations, and a lot of other capabilities. So broadly, I like to use the term information access to refer to these bundle of capabilities. Now, ideally, we want to do it over lots of different types of information, the myriad of information that are available. So text, images, video. And ideally, we like to do it for everybody, ranging from everyday users to domain experts such as medical doctors, lawyers, and the like. However, for the purposes of this talk, I'm going to be mostly focused on text and everyday searchers. All right, so let me deal with the elephant in the room, right? And the elephant in the room, of course, is ChatGPT, large language models, and all the noise that we hear coming from the Atlantic, the New York Times, and the "we're all gonna die" crowd. And so over the past several months, I've had to play therapist to many of my graduate students experiencing this sort of existential angst about what's going to happen. And I'm going to share some of my thoughts on those topics with you right here also. All right, so the TLDR is none of this is fundamentally new. However, we have more powerful tools to deal with all the problems that we've wanted to solve before. And it's a great and exciting time for research, right? So it's not a time to panic. It's a time to look forward to a bright future. And so the bottom line is we should keep calm and carry on, all right? So that really is the message I've delivered it, and so since this is not on the final, feel free to file out the room, and I will see you all for a coffee later or something like that. Okay, but since you're here, I'll continue on with the talk. Let me try to offer a little bit more context and to justify and back up this top level message. Okay, so I'll start with the question of, where are we and how do we get here? Okay, so here's where we are. Right, this is the new Bing search engine, codenamed Sydney, that was revealed a couple of months ago, and it is search as chat. This is the example that Microsoft gave in its blog to launch the whole entire enterprise. Here's somebody asking for a trip for an anniversary in September. What are some places that the search engine can recommend that are within a 3-hour flight from Heathrow? And the search engine gives quite a remarkable result. Well, it says, here's a summary. If you like beaches and sunshine, consider this. If you like mountains and lakes, consider this. And if you like art and history, consider that. It's able to pull a lot of results from the web and synthesize everything together, complete with citations. Wow, amazing. This is the future of search, right? Okay, I'll get into that. But this is, let's start with the history lesson, right? So this is where we are now. Let's talk a little bit about how we got here, right? So before Bing, the dominant mode of search was Google, right? So this is actually from Google at Stanford.edu from circa 1998 or so. And prior to search as chat, a la Bing, we had search as 10 blue links. You typed in a few keywords, you get back a list of results, and you had to sort through it to figure out what was going on, right? Okay, so unwinding the clock a little bit before that, well, this was the time with Google. This was the time when there was digitized information on the web that you could access. Before that was a time when there were digital materials available, but they were not available from the web. So most of you are probably too young to realize this, but in the 90s, there was a time period in which we got CD-ROMs and put them into a machine and booted up something like Encarta Encyclopedia because Wikipedia didn't exist, and that's how we got information, right? Going back even further, before information was widely digitized, there were books, and we were at this stage for several hundred years, right? So libraries dated back to several more centuries before. This is an image from Trinity College Dublin, circa 18th century. This may look familiar because if you're fans of Star Wars, this is where they got the inspiration from for the Jedi archives. Okay, and so if you unwind the clock back even more, you arrive at what I claim to be the first information retrieval problem. So this is a cuneiform tablet from the Babylonian period, circa 700 BCE, and essentially is a record, paraphrasing of course, of Jack owes Matt 2 sheep. Right, so there were accounting records of debts, and they put it in the storehouse somewhere, in the granary somewhere, and then sometime later, when they had to settle the debts, they had to go out and pull out these records. The first information retrieval, the first search problem. All right, so we've been at this for a long time now, right? So the next thing I'm going to talk about is to at least bring some credibility to the things I'm going to tell you about, to tell you where I play in this sort of grand scheme of things. So I've been working on this problem for a while, and a lot of the things I'm about to share I've sort of experienced firsthand. All right, so where do I enter the picture? Somewhere between here and here. So slightly before this and slightly after this. So my own journey began in 1997. So when I began studies at MIT across the river. So this is an image of 545 Tech Square. This building doesn't exist anymore. It used to be home of the MIT AI lab. This is a building right there. Tech Square does not look like that anymore. And so my former advisor, his claim to fame was developing the first question answering system for the web. And I remember I was absolutely floored by this. I remember this is the era of Encarta and the beginning of Google. There was a system where you could ask a question in natural language, like who wrote the music for Next Stop Wonderland, and get back the answer. Or you could ask a question, staying in the entertainment theme, who directed Gone with the Wind, and you would get back the answer without having a bunch of links that then you had to sort through. This was amazing and it blew my mind. And so I've been working on these types of systems and these type of capabilities since around that time. So one of my perhaps most proudest early accomplishments was the following. So ICHCAI is an annual international conference in artificial intelligence. In 2001, so over 20 years ago, it happened to be in Seattle, where Bill Gates was a keynote speaker, very much younger Bill Gates. And one of the things he talked about was Ask MSR, an automated question answering system from information on the World Wide Web. And that was my internship project. I thought that was the coolest thing. So yes, so this explains sort of my place in this sort of long narrative of information retrieval capabilities. All right, so I guess this is all a slightly roundabout way of saying the technologies have changed, but the major problem that we're trying to tackle haven't. It's still about the problem of connecting users with relevant information. Okay, so let's get into a little bit more detail. We, being computer scientists, we like to think of abstractions, and so that's the perspective I'll start to walk you through how these capabilities develop and came to be. All right, so at the end of the day, what we want to build is a black box that looks something like this. In comes a bunch of documents, and there I'm leaving aside what generally known as the content acquisition phase. You got to get the content from somewhere, crawling the web, you got to do data cleaning, and a whole bunch of data preparatory steps. So let's set that aside for now, right? So you get a bunch of documents, you shove it into this black box, and on sometime later on the other end, you put in a bunch of queries, and you get out some results, and lo and behold, they're amazing, and a light bulb goes off, and you're happy. All right, so how do you build this system? Now, as it turns out, we've known how to build systems like this for many, many years, for decades, in fact. Right, so this is the vector space model that some of you are already familiar for doing search. And it was proposed in 1975, although some of the ideas date back even further. So if you zoom in to some of the diagrams that are presented in that paper, some of the figures will look familiar. Here's an example of vector space with query and document vectors. If you pull up the text, what does it say? Well, it says you're going to represent documents by t-dimensional vectors, where each term represents the weight of the jth term. And then what are you going to do? You're going to use the inner product to compute query document similarities, and you're going to do search as a result. And that was in 1975. So we've had some idea how to do this reasonably well for quite a while. All right, so this black box, a first cut at it would be it's something like a vector space model. Let me go into that a little bit more detail on what that actually entails. Okay, so you're going to have the documents that come in, you're going to run them through some type of term weighting scheme, and you're going to get back out a bunch of vectors, right? So here's an example passage. This passage is about the Manhattan Project and the efforts to build the atomic bomb during World War II. And from there, you would get a bag of words representation that looks something like this. I've just written in JSON format, right? So you're going to get all the terms, and then you're going to get weights assigned to it via the term weighting function. Okay, so you're going to take all these document vectors, you're going to shove it into the inverted index, and then you're happy for a while until the queries come in. The queries get represented as multi-hot vectors also in this vector space, and you perform top K retrieval, and you get out the top K results. And then you're happy. All right. Okay, so the TLDR is research, and of course I'm being incredibly unfair, but the research during the 70s to, let's say, the 90s in information retrieval were mostly about how to assign term weights. And at the end of the day, people just said, fine, BM25 is sort of what the entire community converged on. So here's a formula for BM25. It's not important except to recognize that the term weights are a function of things like term frequencies, document lengths, and so characteristics of the statistical characteristics of the terms in the documents they occur in. All right, so that's a high-level overview of what's going on in this black box here. Okay, so let's hop in our time machine and skip ahead a few years. I realized that after doing my slides that many of you are probably now too young to get what this means. This is the DeLorean from Back to the Future, the time machine of a classic movie, but these days when I show this, I just get blank stares. So anyways, imagine a time machine, and so we're hopping from the 70s to not quite modern day yet, because this is February 2023, but just before the previous major innovation. Okay, and what was that? That was BERT. So BERT popped on the scene circa 2018. Right, so what's BERT? Well, BERT is Google's magic pre-trained transformer model. When it came out, the author said it could do a variety of things. It does classification, it does regression, it does named entity recognition, it does question answering, it does your homework, and of course it walks the dog also. Okay, so, but what does it actually do? So Google actually wrote a blog post that tries to sketch out, at least at a high level, of how it applied BERT to search, and this came out in October of 2019, where they describe how they apply BERT to search. Okay. Now, of course, not to be outdone, Bing came back the next month and said, oh yeah, we're using some of the same models too, and it led to all sorts of increases in how effective Bing was. So yay BERT, yay transformer models. Okay, but what's actually going on? So let me share some thoughts with you on that. Okay, so instead of having a single black box, now the architecture we as a community basically settled on is this two-stage architecture, where in the first stage you select some candidate text, and in the next stage you try to understand the text, and I put understand in quotes here. That really means, in the first stage, you use BM25, maybe not literally, but something like BM25. And in the second stage, it really means taking the results from keyword search and doing some type of re-ranking on them. Okay, what does that mean? Okay, let me talk you through it. So this is the usage of BERT in a technique known as a cross-encoder. So here's the complicated architectural diagram of the transformer layers in BERT, but at a very, very high level, what BERT does is it computes a function of two input sequences. So if you read in the original paper, it'll be sentence 1 and sentence 2, and the output will be, are these two sentences paraphrases of each other, right? So apply to information retrieval, you can put a query and you can put a candidate text in instead of the sentences, and you could ask BERT to give you a probability of relevance. And so you're essentially using it as a relevance classifier. So this re-ranking works something like this. You get out the candidate text from the first keyword retrieval stage, and here's BERT peeking in from the side. You iterate over each candidate document. You say, hey, how relevant is candidate 1? How relevant is candidate 2? How relevant is candidate 3? And so on and so forth. And based on the answer given to you by the BERT model, you do re-ranking and you get a better set of results. All right. So the roots of this idea, in fact, go back many, many years. So this is a paper from a journal article in 1989. And just honing in on the abstract, you see, oh, well, it's by an author from a country that no longer exists as an independent entity, just to show you how old it is. And if you read the abstract, it'll talk about estimating the probability of relevance, PR, given some feature representation of the documents. That's what I just told you about, except it was done with BERT, right? So today we'd call this a point-wise learning to rank. Back then they were using relatively primitive features. Today we use BERT to do the same task, and it's much more sophisticated, of course, but the underlying principles are the same. So BERT, of course, is a neural network, but neural networks have been applied for re-ranking and information retrieval for a long time also. This is one of the earlier ones. It probably dates back even further, but already in 1993, people were talking about using 3-layer feed-forward neural networks for estimating query document relevance. Right, so we've been doing this for a while, or at least we've had the aspirations to solve the problem in this specific way for a while now. Okay, BERT. Now, this was the previous major innovation. How does it relate to this Bing thing? Right? So, well, the connection is quite clear. They both draw their intellectual ancestry from transformers. So this is the typical architecture of a transformer diagram. You have the encoder that tries to read an input and generate some latent semantic representations from it that then you feed to a decoder that generates output. So BERT and all these models I'm going to briefly talk about draw their intellectual lineage all the way back to this paper, Attention is All You Need, in 2017. The last time I checked, this paper had over something like 70,000 citations. All right, so transformer architecture was proposed in 2017. The way they trained the model was from initially randomized weights. The next innovation after that was, of course, GPT. Now, this is the original GPT, right? This is the, there was GPT, now we have GPT-4. Before that, we had GPT 3.5. Before that, we have GPT-3. This is the original GPT, right? So they basically said, well, let's take the transformer architecture and that's lop off the encoder part, so it only has the decoder, and then that's add the pre-training using auto-regressive language modeling on top of it. Right? Around the same year came BERT, and BERT was essentially the opposite. They said, encoder, decoder, too much, let's lop off the decoder part, work only on the encoder part, and we'll pre-train it using mass language model as the objective. And then finally, in 2019, came the T5 model that was the pre-trained version of the entire encoder-decoder network. Right? So there is common lineage of all these models that we're hearing today, dating back to the original transformer architectures. All right, so back to this two-step process of doing search, of doing information access. So you select the candidate text, and then you re-rank them somehow by trying to understand, where I put understand in quotes, to get a better result. These days, it's mostly done with transformer-based architectures, encoder-only, decoder, or encoder-decoder. Okay. Now, what about innovations up here, selecting candidate text? Well, so as I've already told you, before it was done using something like BM25, a bag of words term weighting scheme. As a reminder, this is what it looks like. you get back, you feed it a document, you get back a feature vector that looks kind of like this. Now, as it turns out, what you can do is simply rip out the BM25 weighting function and replace it by encoders that are based on some type of transformer architecture. Right? So this works by feeding the transformer a large number of query document pairs and essentially asking it to do representation learning. Right? So you're asking it, so you see a query document pair, I want the similarity to be close together, and you see a query and a non-relevant document pair, you want to push the similarity apart. And you do that with neural networks, you learn good representations for queries and documents. Right? But it's very much the same high-level design. Instead of a bag of words a representation, you get in you feed it the model a piece of text, and you get out a dense vector representation, typically something like 768 dimensions of real value to pick random numbers, and that's the representation, where putatively the dimensions of this vector represent some type of latent semantic meaning, but don't read too much into that. Okay, so this is, if you hear the large, the discussion about vector search, that's what people are talking about. It's nearest neighbor search over query vectors using, over document vectors using a query vector. So you have a bunch of document vectors that are encoded by a transformer-based encoder. You have a query vector that comes in, and you're still doing top K retrieval. All right. So transformers have been used in search since 2019. Right? So even though you just heard about ChatGPT a few months ago, the same type of technologies have been deployed in Google, at Bing for several years now. All right, so the next question I want to address is, well, what really is the big advance from this to what came before? The mode of searching we know by the phrase, getting the 10 blue links. Okay, so I like to talk about abstractions, so that's go back to boxes and filling in boxes. Okay, so at the high level, what is ChatGPT? It's a large language model. It's fed into it a pre-training corpus and some instructions, right? So step number 1 is autoregressive language modeling, and step 2 is instruction fine-tuning using reinforcement learning with human feedback, right? So you build a large language model, and you feed into it some type of prompt, and you get out some type of amazing response, a completion is what they call it. So how does Bing work? Well, Bing is, this is the new Bing search, is using a large language model. We now know that it's using GPT-4 behind the scenes. So in comes a query, and out comes amazing search results, like the example I just showed you a few slides ago. But how does it actually work? Well, it works by talking to a retrieval model. Right? So the query comes in, the language model does something, it sends a query to the retrieval model. The retrieval model does some searching, returns a result, and the language model post-processes it. Okay, I'll give you an example exactly how that's done in a bit. But I want to open up this black box and ask the question, well, what's going on here? Well, in fact, I just spent the last 20 minutes telling you what's going on in that box. All the things I discussed, transformers being used in search since 2019, well, all of that is now squeezed into this box. All right. And so this is generally the approach known as retrieval augmentation. Right? The large language model is not doing everything by itself. It's calling out to a retrieval model that's supplying with it the candidate text that in the later post processes in a way. Okay, so retrieval, in other words, forms the foundation of information access using large language models. Right. You don't have to believe me. This is exactly how Bing works. If you go read their blog post, oh, the URL got chopped off. But the Bing's blog post exactly describes this type of architecture. They have an orchestrator on top, but it's essentially GPT talking to a retrieval model. In their case, the retrieval model is the Bing search engine. Okay. Bing calls this grounding, and I'll illustrate the sort of the effects of grounding using this example. Okay, so without grounding, without retrieval augmentation, you could just ask the large language model something like this. Tell me how hydrogen and helium are different, and it'll give you something reasonable. If you want something better, what you could hand to the large language model is a prompt that looks something like this. Given the following facts, tell me how hydrogen and helium are different. Okay, and you put in a bunch of facts about it, and it will construct an answer that is much more to the point because you've told the large language model, I want the answer, but I want it grounded on this. This is what retrieval augmentation provides. Right? So thinking now in terms of, so rolling it back and not talking about Bing and ChatGPT in particular, I'm going to spend the next few minutes talking about this interaction a little bit more. What are the roles of large language models and retrieval? Okay, so to explain that, I have to make a confession. All right. And the confession is that I lied. I lied mostly in omission.
Did you hallucinate?
Yes, I hallucinated also. So what is the problem that we're trying to solve? In the first slide, right, I stated, I want to solve the problem of how to connect users with relevant information. But what I forgot to add is like, why are we doing it? All right. Why? That's the critical omission. Okay, so some of our colleagues have expounded on this at length. So Nick Belkin, a senior information retrieval expert, would say something like, well, we want to connect users with relevant information to support people in the achievement of a goal or task that led them to want that information in the first place. Okay, so some people would say, we want to connect users with relevant information in order to address an information need. I think that's accurate, but I think it's kind of circular. You want information because you have an information need. It fits, but not ideal. Okay. Some people would say, well, we want to connect users with relevant information to support the completion of a task. That's actually very practical and accurate, although it's not particularly aspirational, right? We want to connect user with information to do a task. Okay, so what I really like is what my colleague Justin Zobel says. We want to connect users with relevant information to aid in cognition. Well, now that's something aspirational that we can all latch onto. Now you say cognition? Seriously? Isn't that too grandiose? Absolutely not. If you look up the dictionary definition of cognition, here's what it says. This is from Merriam-Webster, I believe. It's the mental action or process of acquiring knowledge and understanding through thought, experience, and the senses. That exactly explains what we're trying to do. Okay, so looking at the broad picture, I focused on this black box, but in fact, I've drawn it too big. This is the cognition process, right? I've drawn it too big. In fact, it should actually be cut down to size because the actual process by which you get results exists in a broader set of activities of which that's just a small piece. Okay, let me walk you through some of them. Okay, so for example, the query has to come from somewhere, right? the query comes from somebody with an information need. So the information need or needs to come from some abstract information itch that I want to scratch into something that I actually type into a computer keyboard or talk into my device, right? We haven't actually invented mind-reading computers yet, not yet. So we still have to go through that query reformulation process. Okay. How often is it that you get the results and you're like, oh, that's it, I'm done. I got exactly what I needed. No, that doesn't happen. So there's this interactive retrieval process where you read the results and you're like, oh, that's not quite right. I don't want that. Oh, here's an interesting keyword. Let me put it back in the search. Right? There's this interaction loop that goes on. When you're doing this in the context of some task you're trying to accomplish. This is, once again, it got cut off in the slides, but this is a task tree diagram from a recent paper by Chirag Shell et al. And so it's trying to show that things that we're trying to accomplish can be hierarchically decomposed, right? So for example, you're trying to plan a vacation. What are the subtasks of that? Well, you got to figure out where to go first. You got to research each destination. Then you got to book the flights and the hotels and the activity and so on and so forth. And it can be decomposed into a tree-like structure. And each one of these subtasks might be on different devices. I may start with on the browser and then come up with a brilliant idea and ask some questions on my phone, and then move back to the computer for some other types of tasks. But this may occur temporally distributed over days, if not weeks. Right? And of course, there's synthesis, right? So you have multiple queries. You got to look at the results, pull in the relevant portions, and synthesize them together before, and all of this needs to go round and round in an iterative manner before you finally get the task completion and have that light bulb go in your head. Right? So previously, we've been focused mostly on this. Why? Because it's the part of this whole broader processes that we can make headway as computer scientists. But the cool thing is, now with large language models, we have the tools to be able to tackle the other parts around just the core retrieval black box. Right? So, and in fact, this is where the Bing interface is trying to go. Okay, let me talk about some specifics, right? So, before we had large language models, in the Google search engine 10 blue links view of search, you had to come up with query terms yourself. You got to look at the results. You got to say, that's a good query term. I'll plug that in. Oh, that's a bad query term. I'll throw that out, and I'll iterate with another query. With large language models, you get much more natural interactions through natural language. So that's one key difference that LLMs have improved the process. Here's another one. Before, you had multiple queries and multiple results. And you all know this. Each one appears in a browser tab. And you have a browser window that has way too many tabs. And you are going through the tabs, trying to synthesize a result. Now, you get some level of semi-automated synthesis that's aided by the large language model. Right, let's talk about this. Before, you had to manually keep track of subtasks, right? To plan a vacation, you had to do some preliminary research, and you got to dive into each one of the options, and finally, you got to make the reservations. With LLMs, it'll try to guide you through the process in a helpful way, and that alleviates a lot of the burdens on essentially navigating this task tree. Right. So this is where Bing wants to go. But of course, none of this is fundamentally new. Let me just give you some example. So here's a paper from Computational Linguistics Journal in 1998. This was 25 years ago. It's about generating natural language summaries from multiple online sources by Drago Radev and Kathy McEwen. Okay. Here's another work. I don't need to tell you the date because it's already up there, and this is from over 15 years ago. And it's the task overview from one of these benchmark evaluations that are community-wide. And if you look into one of the paragraphs, I've blown it up. What is the task? Well, the task is answering a complex question, synthesizing a well-organized, fluent answer from a set of 25 to 50 documents, and it has to be more than just stating a name, date, or quantity. And summaries are evaluated for both content and readability. 15 years ago, we were already trying to do this. And then even the idea or the metaphor of information retrieval as chat, this goes back even further. This goes back decades, right? This was a time before you couldn't use a search system yourself. You had to go to a library and talk to a librarian that did these mediated interactions with you. They conducted with you what's known as a reference interview, right? They asked you questions about the stuff that you're trying to find, and they were the ones that were trying to access the online databases behind the desk, right? So Bing is getting its metaphor from something that is decades old. All right, so coming back to this, right? None of this is fundamentally new. But the key point here is these large language models allow us to do everything better. Before, these goals and these capabilities were more aspirational. Now today, with large language models as a tool, we actually have the capabilities to execute on this vision. And that's why I think it's really, really exciting. Let me give you an example, right? So back in 1998, when Radev and McEwen were working on this multi-document summarization, at a high level, it worked because they did a lot of manual knowledge engineering, right? The system had a lot of templates, essentially ontologies that were manually engineered. The system was designed to summarize events, a specific series of events related to terrorist act and the like. And it was only with the aid of these knowledge templates that we were able to make headway on the problem, right? So as soon as you fed in personal interest stories or something like that and wanted the systems to summarize those, it basically fell apart. Okay, so today, we don't need this knowledge engineering, right? LLMs allow us to execute on the idea, but do it in a much better way. Okay, so the message I'm trying to convey is that before, we were focused primarily on this box because that was the part of this broader information ecosystem that we could most easily make progress on, all right? But with LLMs as a tool, we can now tackle the entire problem. Okay, let me start to wrap up by giving you a few examples. Okay, so here is an example from Bing search not doing so well. So this was on a tweet thread that I pulled off Twitter a few months ago. All right, so the answer that it's trying to give is recommend me some phones with a good camera and battery life under this particular budget. And you see in the answer, it makes a lot of things up. It just doesn't get it right. So gets the price, doesn't get the price right, doesn't get the price right here. It thinks the camera has a wrong megapixel count, the wrong battery size, so on and so forth, right? We know this today as the hallucination problem. Right? It's gotten better, but it's still not solved. But I think we have the tools to solve it. Retrieval augmentation that I described to you is the most promising solution to this challenge, in my opinion. Right? So instead of, recap, asking how hydrogen and helium are different. And this is the working example. We tell the model, the large language model, to tell me how hydrogen and helium are different given all these facts. And if you hand it a bunch of facts, it's far less prone to hallucination, right? Well, what's that? Well, that's this box. And so this is what I say to my students. We've been working on this for a while. Today, it is not only important, but it's critical, right? Because we all know the garbage in, garbage out phenomenon, right? So if the grounding, the facts that you're trying to feed to the large language model are garbage, you're going to get garbage output, which makes the retrieval component, as I said, not only important, but essential. Okay. But this also means that the large language model, once it's gotten the facts, shouldn't screw it up. Right? That's another complementary line of research that we need to explore further. Okay. So none of this is fundamentally new. LLMs allow us to do it better, and there's still plenty left to do. Now, let me circle back to this problem that we're trying to solve, right? How to connect users with relevant information to aid in cognition. So let me step up at an even higher level. Okay, so at the end of the day, we're starting with some artifacts, digital or maybe physical, and we're going through some process, and at the end, on the other end, comes some type of cognition, some type of greater understanding that we've gotten. And in the beginning, this was all mostly via human effort, manual effort, right? With technology, what we've noticed is we've gotten more and more system assistance. Right? With each new generation of technology, we've gotten more and more system assistance. So the interesting question is, now that our tools have gotten better, what happens? Right? Do we all become fat and lazy like Wall-E? Or is there an alternative future? Well, so one simple answer is that we now become far more efficient. Right? But I think the better answer is that these tools free us to do more, to tackle tasks with greater complexity. Right? So I don't think it's about AI, artificial intelligence. It's really more about IA, intelligence augmentation. So all of this I've been hearing about AIs replacing humans, that is not the right discussion to be having. It's not about replacing. It's about assisting and augmenting human capabilities. All right, so coming back full circle, right, with so much noise from ChatGPT, LLMs, and the we're all gonna die crowd, where are we? Well, you already know the answer. So the TLDR is, none of this is fundamentally new. People have needed access to information for literally thousands of years. Transformers have been applied to search since 2019. Multi-document summarization is at least 20 years old. And this whole idea of search as an interactive dialogue dates back even further, right? Technology has augmented human cognition for centuries, right? But the key difference now is we have more powerful tools. We have more powerful tools to make us more productive and to expand our capabilities, and there's still plenty left to work on. Okay? So the message is keep calm and carry on, but the more optimistic version of that is actually it's an exciting time to do research. Right? And that's all I have. I'd be happy to take any questions.
Okay, so do we have any questions? All right. So here the rules are: you got to speak into the shiny part.
Okay. All right. Hello. Okay. You mentioned something about query reformulation, right?
Sure.
In the beginning, we used to type in something into Google,
Yep.
find something else,
Mhm.
and not be satisfied,
Yep.
reformulate it.
Yep.
With large language models, we have a very similar type of procedure with prompt engineering, right?
Mm-hmm.
You're trying to engineer the prompt,
Mhm.
get some results,
Yep.
not being happy with what you get,
Yep.
and then re-engineering the prompt.
Sure.
So how does it exactly solve the problem of query reformulation?
So the question is, you're saying that before you just put in keywords and change the keywords, and now today, well, you just try a prompt and the prompt didn't work, and you got to try another prompt. So how have things gotten better? I think things have gotten better because the model's better able to understand your intent. And so the amount of low-level fidgeting with the queries has decreased. And so I think what you're trying to do with a prompt is try to alternatively formulate your information needed, what you're trying to do at a higher level, right? So it's not choosing the right keywords. It's about, well, that tone is not quite right, so I want to change the tone. So in that way, I think it's an improvement. So that's sort of point number one. Another way to address it is that, look, prompt engineering didn't exist 3 months ago, right? So we are in the beginning of this revolution, right? So learning how to do better prompt engineering is like learning how to better search Google in 2003, which was a valuable thing. People didn't know how to search Google. And so in some ways, things have changed, and in some ways they haven't. Does that answer your question?
Absolutely.
Okay.
Okay. Here, excuse me. Oh, gee, I could really mess things up there. Yeah, right. Can you pass this back? You got it.
Thanks so much. Very interesting, and I like how you sort of laid it all out. I think in the beginning you sort of said there was this process of document collection, and I'm wondering, it seems like that plays an even more important role when you start to get to these like use case specific. So if you're talking about, a travel company might have to collect their documents in a particular way, fine tune the model in a particular way, and so I wonder if you have any thoughts about that process and the role that that process plays in sort of the development of these.
So the answer is you're absolutely right, right? And this all goes back to garbage in, garbage out, right? And so people have expressed concern about the data that's being fed into these large language models. Number one, we actually don't know exactly what GPT 3.5, GPT 4 is trained on. We have some idea. But we're pretty sure it's ingested a large portion of the web, including all the toxic material that's found on the web. And so that is a point of concern. But I think as we move forward and these technologies become more and more commonplace or commoditized, I think it will become more and more practical to essentially train your own models. So there are not quite as capable, but fairly capable open source models that you can download, the so-called jailbroken llama models, and some other open source alternatives like Dotty is a one that people have been playing with that you can download, and you can further pre-train on your own internal data. You can change the alignment by doing your own instruction fine-tuning. And so I'm optimistic because there are a lot of options to solve all these problems. Yeah.
So,
All right. Hi, Jim. Thank you for the really interesting talk. So you were presenting or discussing the idea of using retrieval to improve manage a little bit the hallucinations of large language models. So what went wrong with Bing? Because Bing has this very architecture that you were mentioning, but it still had all these factual errors. So
okay. So there's a separate question of whether or not Bing and all these technologies were deployed prematurely. All right. So I think that's one of the concerns here is that these large companies may have perhaps rushed the models out to market before they were quite ready, right? So, but you'll notice in the slides that I have up that there were actually two steps, right? The first is you gotta give it good grounding, right? So if you retrieve misinformation, the language model is gonna spew out more information, right? If you actually gave it articles from the New England Journal of Medicine and asked it about vaccine effectiveness, for example, it's going to do a reasonable job. However, I was very careful on top that we got to make sure the language model doesn't screw up the facts that you fed it via the retrieval augmentation. And things are getting better, but we're not quite there yet. But I think this is a technical problem we can make progress on. Does that answer your question? No. Oh.
So I'm going to queue up a question from the web, the last one we saw. But before I get there, I want to sort of set it up with the hallucination problem is clearly a big problem.
Correct.
And I think you were outlining a solution, which is that we want to identify each of the facts in the statements, and then we want to attribute all of the facts to something that's credible. And so that's sort of a attribution problem or retrieval problem.
Yep.
Now, could you read the last question we have coming in?
With enough precise context included, LLMs might have a better factual response. As there are numerous KG databases and other forms of knowledge, do you feel we can make LLMs respond with facts efficiently? And what's your suggestion for dealing with this?
Oh, absolutely. I have to thank the asker of the question. In giving these slides, there's always things that you have to call that's sitting on the cutting room floor. But the more general form of a large language model, depending on a retrieval model, is a large language model depending on external knowledge sources and external APIs, of which a search engine or a QA engine is one. Right. So there's nothing to prevent the large language model from querying a SQL database, from issuing a Sparkle query to a knowledge graph, from issuing a query that is that gives you a real-time feed of the latest scores from last night. In fact, that's exactly how Bing is able to answer questions about the game last night.
Okay.
So that's a very promising area of future work.
Wonderful. Thank you for the very nice talk. I wonder, and this is more on the retrieval augmentation stuff. So we have these two components. We've got these giant LLMs. We've got retrieval models that do a pretty good job, but they're totally decoupled. And so I wonder, I completely agree that, retrieval augmentation is likely a path forward to addressing some of the hallucination issues, but nothing in the standard LLM objectives, encourage or, necessitate that the model actually pay attention to the context with which you are prompting it, right? And so I wonder if you have thoughts on perhaps better pre-training objectives for the LLM component that enforce that as a constraint by construction, or if you have other thoughts on how do you actually realize that kind of criteria?
Yeah, that's a really good question, and it's something I've thought about. So I at least can restate the problem in a slightly different way. So whenever you have these decoupled components, you lose differentiability, pretty much, right? And as soon as you lose differentiability, you lose a lot of what makes these techniques work, being able to train end to end. And so various people have been trying to have their cake and eat it too, right? So attention mechanisms that allow you to access the external knowledge sources directly. There have been various attempts along those lines. They're all promising, and I think you're answering part of my same question. That's another example of why this is such an exciting time to do research right now. Does it help? Yes, I think I know what the problem is, but I don't have a solution. And if I did, that would be my next NeurIPS paper or something like that, right?
Thank you so much. It was it was really nice to know your views. I would also like to ask you, without losing differentiability, is there a way to get the biases out of these models that generally creep in? And I'm sure you were expecting that question.
Yeah. So, yes. I think what gets lost in this discussion about biases and more generally the question of alignment is that we often lose sight of the fact that I think at the end of the day, we're going to need models that are aligned differently for different tasks, for different audiences, based on different cultural backgrounds, different expectations, different domains, etc. So I think it's less helpful to talk about, how do we get bias out of the models in the general case, and focus more about how do we get bias out of the models for medical diagnoses, for job recommendations, for particular downstream tasks. I think if we start to look at the problem from that perspective, it becomes a little bit more tractable. Does it help?
Yeah. All right. So I think we're sort of out of time, but I did want to sort of end with one note. I have some students who are feeling a little discouraged with all the hype they're hearing. They're kind of wondering if it's sort of pointless to be studying this stuff anymore because it's all been solved. But I kind of suspect that your program, the IA program, is probably going to take about as long as the other programs you described. So do you think it's going to happen before you retire?
Yes. No, I don't think
You're
so.
on the record here.
Yeah. So what's going to happen? I mean, in the sense that our tools will become more capable and we'll be able to do more. So from that perspective, this process will be never ending. Yes, in the sense that the problems that we think are problems today, I think they'll be solved by the time my career comes to an end. So for example, I think the hallucination problem is, I'll say this on the record, is not going to take as long to solve as we think it is, because the way I've formulated as a retrieval augmentation problem where the language model's job is just not to screw up what the retrieval module gave it, I think that's a much more tractable problem. I think with respect to bias, if we start thinking about properly lining the models for particular downstream tasks, we're going to see these problems solved in a much more tractable manner.
You'll have to repeat any of that.
So what about AGI? I anticipated this question and I addressed it at the very, very beginning, right? So for the purposes of my own research program, what I'm interested, I just want to connect people with the relevant information that they want. To be honest, I really don't even know what an AGI is. I have today not heard a precise definition of what an AGI is. And so I say, people can do other things like unravel the mysteries of consciousness and build AGIs. I'm going to focus on something that I think is much more practical, but still very impactful.
So let me end by, I'll go on the record and say I think you're wrong. I remember there are recordings of people in the 50s saying that all the problems in machine translation will be solved in 5 years. It's 50 years, more than 50 years later, and we're still working on it. So I have a feeling that this is a good time to be studying this stuff because there's no problem about employment. You're going to be busy. I think you'd be lucky to get to the progress you have in mind before you retire. All right. But anyway, we'll see if you're right or see if I'm wrong when you retire at your retirement party. We'll have this discussion.
Great.
Let's thank the speaker.